Right, so our new topic is on loops and variables. Loops and variables as a way of storing the value of something to be used later in the program, and loops as a way of repeating parts of the program over and over. And there's two ways of doing loops, and we'll also see something about constants when we're talking about variables, I guess. Okay, so repetition, it's one of the fundamental components of programming, is that you might remember we have sequence, which means that a program will proceed from the first line to the last line in order. Repetition, we also use the word iteration, means that we can repeat a part of a program many, many times. It has these benefits. I mean, because we have the ability to repeat things, we can take advantage of the great power of the computer to do things very quickly. And so we can repeat a simple task very, very quickly. You probably, when you went to buy a computer sometime, you've come across the term gigahertz, megahertz, this type of thing. A hertz is a cycle in a second. So if you have a gigahertz, that's a billion cycles in a second. And this is kind of the speed that we're talking about processing in computers. So billions of cycles in a second. That doesn't mean you can do a loop billions of times in a second, but certainly it's fast enough now that you can do them millions of times in a second, or hundreds of millions of times in a second, because there's lots more than one computer cycle required for a loop, generally. But computers can do things very quickly, repeating, and so looping helps us to take advantage of that. And that is made there twice in that slide. Okay, so you may remember this from a previous lecture. The idea being that we've got the oval type structures there representing start and end of an algorithm. We've got the rhombus type thing, which represents an input or an output. And this is an output. And this is trying to show that that output is being repeated many times. Now, this flow chart is not complete because we don't have the control structure, which is needed in between the output there and the arrow going up. But so we have that control structure. Maybe you'll remember that. That control structure was a diamond. So we use a diamond to represent that, and we'll see that in a minute. So the diagram did show, even without the diamond, that the flow of the diagram, which was represented by the arrows in it represent how the flow of the algorithm is working. That flow can be changed. We can branch. We use that term branching. We can branch that flow so that it goes in one direction or another. And so we have choices that can be made there. And this is how we control looping. This is how we control repetition in our computer programs, is we have some kind of choice that's made at the point where we want to do the looping, and that's how we control it. Now, there's two different types of choices that we can do there. We can have something which is counted. So we can say, at the start, we can predetermine that we're going to do this so many times. We can count it, and then we can just measure the count. And the other way we can do it is we have this thing called a sentinel. A sentinel is kind of like a guard. You may have heard that term used in non-computing context before. A sentinel is a guard to stop access to usually it was by sentinels were used in armies or castles, that type of thing. The sentinel would stop access to people who are unauthorized. So in a computer program, the sentinel, what it's doing is it's controlling access to the loop. You know, do we want to get in the loop, or do we want to get out of the loop? The sentinel will control that access. So a counted loop, remember I just said that there's two different types of loops. We got the loop which is counted. So before we start the loop, we say how many times we're going to do it. We predetermine how many times we're going to do it. Then all we have to do is we have to count. Now, to do the count properly, first you have to set a initial value. which would be like 0. And then you count until you get to the number of times that you want. And then at that point, you'll start. So every time you go through the loop, you must measure how many, what is the count. And when you arrive at the count that you want, then you stop. So here would be a counted loop for this. Now, this is not quite complete, I guess, because we should have put an initial value here. And then we will count here. To be honest, I would have done this different. I would have said the number of iterations is less than 10, because when it becomes equal to 10, we stop. That's what this is saying. When it becomes equal to 10, we stop. So as long as the count is less than 10, the other thing that you need to do is have another thing here which incremented the count. So this is showing a development of this type of an algorithm, kind of one step at a time. The algorithm is not yet complete because we haven't initialized the counter, and we are measuring the count, but we haven't initialized the counter and we haven't incremented the counter, but we'll see that in a minute. And in fact, there it is. So to make it to work properly, you have to have these 2 extra steps. You have to initialize the counter. Initialize means set to its first value, the value that we're going to start with. We're going to start with, usually in counting, we can start with a number of 0. And maybe I can move this down so it doesn't need to be there. We're going to start with a number of 0, and we're going to keep counting until we get to 10. And when we get to 10, we stop. And so we must measure it at the end. But if we start with 0, after we do the process that we're going to do, we must increment the count. Increment means to add by small amounts. The small amount that we would use in this would be 1. So that's the way you count. Counting means adding 1. All right, so here's an opportunity for us to try this. We could try to do a flow chart, and I'm sorry, I don't know if I've got a proper pen to do this with, but I'll try. To do a flow chart that asks the user to enter their age, happy birthday to you, how many times? So if you're going to do something like that, oh, well, it's flow chart, right? So we're going to have a start, and then we're going to initialize the variable, the counter, which is a variable. Initialize counter. To 0. Then we have to, so that's a process. It's not an input or an output. We need to get the person's name. Oh, sorry, get the person's, is it their, do we need their name or just their age? Just their age, get age. So that's an input. And then we're going to print, a happy birthday. So that's an output. And so that's an output. So I'll do that like that. We'll print happy birthday. And then we need to increment the counter. Now, that means take the counter. The counter is equal to count plus 1. Count takes the value of count plus 1. That's what we mean by increment. We're adding 1 to it. Increment means add a small amount. We're going to increment the counter, and then we're going to test the, sorry, I'm running out of room here. Maybe, but this happens. So I'm going to draw an arrow that goes from there to there, and we're going to do a test now. Problem is my arrows are going to be crossing. Maybe I'll draw the arrow this way. The arrow goes from there to there. And then we have a decision. And the decision is the count is less than the age. So I'm doing a little bit different than the example that we had. The thing, but is the count less than the age? If the count is less than the age, then we go back to here, print happy birthday again, okay? If it's not, then we're finished, and so we end. So that would be a counted loop. Counted loop, let me just summarize that again. At the start, we initialize a counter, set it to a, it's always going to be a value of 0 or 1. Well, almost always. No, it doesn't have to always be. It's, for this, it's going to be. We get their age. How old are you? Now, here's the processing that's going to be repeated. Do you see that the arrows keep going through that? Right? This part here is going to be repeated until the age. So this is a no, and this is a yes. Until the age finally is no longer, sorry, the count is no longer smaller than the age. Then we stop. And so that will print until we get to the person's age. Actually, it might be age plus 1. No. So that's one type of loop. Two types of loops we need to consider: the counted loop and the other loop. Now, actually, before we go on, we should just test this to make sure that that's going to work. So if we started with 0, yes, that will work. The thing that I was worried about is maybe we're going to print 1 too many times, but we don't actually. We increment the count after we print, so it's okay. So it's supposing the person is 25 years old. We print up until we get to 24. When we get to 25, so we printed 0, then we printed 1, 2, 3, up to 24. That's 25 times because we're counting 0, right? And then when they get to 25, the count is no longer less than the age, and so we stop. So that would actually work. The Sentinel loop is the iteration of code, so with a specific value is entered. So what we do here is we're going to have a choice given to the user of the computer system. So the computer system will have some kind of thing that every time we run the loop, we give the user a option to exit. And so this is it's a little different than the counted loop. In the counted loop, we knew how many times we're going to do it. In the Sentinel loop, we don't know. We're just going to go until something happens. Now, I said the user could enter it. There could also be some kind of system input that would come and exit the program. So we use it for times when we don't know beforehand how many times we're going to do the loop. That sort of comes up at the during the processing, and so we have some way of capturing that with a variable which we'll call a Sentinel. And when the Sentinel has a certain value, then we exit the loop. So example, if we wanted to compute daily sales in a retail shop, well, when are we going to stop? This is the question that we're trying to answer, right? So if we keep getting new values for the sales amount, when are we going to stop? We might never stop if we don't put in there somewhere a diamond in our, we call that our decision block there. We have to have some kind of decision. Are we going to continue or not? And that isn't here yet. So we can see that this is not quite complete. So we don't want to have an infinite loop. You could get an infinite loop if you did this. Actually, that was kind of the very, very first denial of service attacks. Would have been infinite loops of pinging somebody's router or something. I don't know, any of you guys doing networking? Interested in cyber or anything like that? So anyways, infinite loops can be quite bad because they will keep processing until you turn off the program. So we don't want an infinite loop. So we want to have something in here, some decision point, so that we can know when to stop. So what we'll typically do is we may ask the user, do you want to keep going? And that they will put some input, and from that we will we'll know. So you can see that something's missing here, because here we've got a point where the arrows can go in 2 different directions, but there's no decision point to check that. So let's go and see how that would work. We could put in a Sentinel value of 0. So we ask the person to enter in the current sales for the day. We know if the current sales are 0, that's our sort of code. You can think of a Sentinel value as a special code that we use, like the secret password or whatever. It's a secret password that we're going to use to get out of the loop. And so if we say, okay, so what's the password? The password's 0, so we stop the loop. Otherwise, we keep going. And so now the flow chart is more complete. So let's go through it and see if we can follow that. What is the current sale amount? This, if you remember back a couple of slides, this was all we started with, right? We were just going to keep on getting the current sales amount. We're going to add it to the total sales amount. And we just keep doing that until we stop. But how would we know how to stop? That was the problem. So we got this special code or Sentinel value that we decided if the user entered the value of 0, we'd know that we're supposed to stop. And at that point, we will just print what is the total. Now, later in this lecture, we have to talk about variables. And you can actually see 3 variables here, right? We've got total sales, well, 2 variables. Well, 3, I suppose. Yeah, current sale, 2, sorry. We got total sales and current sale. These are variables. Variables can be set to a value. So variables occupy a place in the memory. And we set them to a value. And then the good thing about that is we can output that value when we require it. We'll see that in a minute. So our Sentinel there was 0. Let's talk a little bit about Sentinels. So it should be a value. So I called it a secret code, right, to get us out of the loop. But it should be a value that's not going to turn up in the ordinary processing of that loop. So we chose the number 0 there because people don't normally have a sales value of 0. You could choose a negative number. That would work really well because nobody's going to have sales value of negative. And so any negative value would work fine. And often people will do that. So you don't have to, you could have the loop. You don't have to have an equality in your decision that ends the loop. You can have an inequality like this, where you say, well, if it's less than. So you could have just said, if the sales value is less than or equal to 0, then we exit the loop. And so we're not looking for an exact amount. That would have worked too. All right, so let's look at this one. Flowchart for a program that outputs, I will not cheat in my assignments. Then ask the user if they want to print it again or stop. So this one is going to print until we get tired of printing. It's going to print. Okay. So sorry about this. I'm going to erase it. A very bad color is green. I should have brought a pen. I'm sorry. You're supposed to do this. Maybe you guys can help me with this one. I've been kind of pushing on because I decided to record this. It's always going to have a start and an end. And the thing is, we're just going to print, I will not cheat on my assignments. So we're going to do that at least once. So this is just going to be an output. I could say print. I will not cheat. So we're good. But the thing is, we're going to do that until we get tired of doing it. So you guys help me. What would I put next? Yeah, okay. So we could put a decision, which is, do you want to finish? Okay, we need to accept. Yeah, okay. So this is a flow chart, so we can just do it like that. You say, do you want to finish? So we could just accept yes or no, right? And if it's yes, well, let's say no. We don't want to finish. So what do? Just go back up there. And if it's yes, then we end. So that's not too hard. If the user says it will loop. So when do we use a counted loop? When do we use a Sentinel loop? If we know how many, at the start, if we know how many times we're going to do something, we could use a counted loop. So for example, if you're the tax office, I'm trying to get an example that works here, but all right, here they have taxes, but the taxes are on sort of things that are bought and sold. people don't pay income tax, right? So, but yeah, okay, so taxes. What we could do is we could, let's say we wanted a report of all the taxes. So what you could do is you could have a file which has all of the transactions that occurred, and you could count that file. And once you've counted it, that would be your counted value. Then you could use a loop to process each one of those until you had done all the processing of all of them, right, by account. If we don't know how many times we're going to do it, then we could use a Sentinel loop. Obviously, you have to be careful in managing the counter. So how we manage that counter is you must set it to an initial value, you must increment it, and then you must test the value at the end of the loop. In the Sentinel loop, no counter, but you have to be careful what you're going to choose as your Sentinel value, something that is not in the normal range. All right, so at this point in the lecture, we're going to look at something just a little bit different, but though very much related, which is the idea of memory and variables. So you'll remember when we talked at the start of this course about computer architecture, you know, the Van Neumann architecture, et cetera, that memory is very important in that architecture. Even in the CPU, there's memory registers, which we saw come up as a question many, many times. Then there was the cache, and then there was a primary memory, and then there was a secondary memory. So memory is important to computer processing. It's important as a temporary storage of information that we're going to use in our computer. So temporary storage of values. And we do that best with things called variables. And so variables will be assigned addresses in the memory. So there's a unique address for each variable. Then values are assigned to those addresses, and then those values can be referred to and retrieved later. Right, so something similar to variables is a constant. So a constant is just like a variable, except you'd guess by the name, it's called a constant, that its value doesn't change. Whereas a variable, throughout the time of the computer programming process, the variable value could change many, many times. A constant, the idea is that throughout the running of the program, that value doesn't change. So usually at the start of our programs, we're going to define our variables and we define our constants. And yeah, the constant, as I said, just won't change. So for example, there's some mathematical constants that could be used, but there's lots of other constants that you could sort of have as part of your computer program. Mathematical constant, for example, pi, it's actually sort of built into most programs. But if you wanted to calculate using a computer, the radius of the circumference or the area of a circle, you would need to use some combination of pi and the radius. So for example, the radius squared multiplied by pi gives you the area of a circle. And so pi is constant. You would set that at the start of your program. But the radius of the circle would be an input that you would get from your user. So you'd ask them what the radius was, and then you could output, well, then you would calculate the area, then you could output the area. So that brings us to the idea of how do we name things? And this is sort of just general computing standards. We use a naming standard in the way that we name our variables and our constants. So one of the things we don't do is we don't put spaces in the name in the middle of the name. We can use underscores or even dashes, but we don't put spaces in them. The other thing is we're careful with our capitalization. So with a variable, the first letter and most of the letters of the variable name should not be capitalized. So we have this standard, which we refer to as camel capitalization or camel case, lower camel case. The idea there is that if you want to have names for your variables and constants which are meaningful, so that somebody else who reads your program later, and also you, if you come back and read the program 6 months later, and after you've created the program and you want to see what's happening, you should the names of the variables should be meaningful, so that as soon as you read the name, it's obvious what it is. And so that might mean that we might end up with variables that more than one word put together, but we don't put spaces between the words. What we tend to do is we use lower camel case, which what that's going to do is it's going to capitalize the second, third, fourth word, the first letter of that word, but it won't capitalize the first letter of the variable. So here's an example: student name. Notice there's no capitalization of S, but there is a name, because otherwise, if you didn't put that capitalization on the N, it would just be hard to read it. It's sort of, you look at that and you can see, oh, that's student name. And so we call that camel, lower camel case. Why? I hope it's obvious to you. Camel has a sort of a hump in the middle of its body, which is sort of higher than other parts of his body. So that represents the capitalization. With constants, we tend to capitalize the entire name of the constant. And so there's two different ways of approaching that. Now, I say that's standardization. Will your program work without this? Yes. You may have some problems with Java if you capitalize your variables. So don't do that. So, I mean, basically just do this the way that it says, right? Most computer programs would accept it if you did it other ways. So it's not so much a sort of a syntax thing. It is in some computer languages. It's more of a standardization, which makes it easier for you to read. So that should be not only in your computer program, but also in your written pseudocode to explain the algorithm. Okay, so here's a little bit about the types of values that can be stored by variables. And so we've got a couple of different types of numbers, integers and floating points. Now, I should say a little bit about that. Integers require a lot less storage space than floating points. Floating points take a lot of space because they have the ability to store decimal places that may run to many, many points. So it takes a lot more memory space. That used to be more of a concern than it might be now, because that would affect the efficiency of your program. But I mean, if you're just going to be counting, it's better to use integer for that, right? If you're counting whole units, don't use a floating point. But if anything's ever going to be divided, or anything is the result of a division, then you would definitely need to use floating points for that. Not for the thing that's being divided, but for the thing that is the result of that. Characters, so this represents individual characters, like any letter of the alphabet. We have an ASCII code, which represents characters. You should become familiar with that at some time, ASCII. ASCII code, there's two versions of it. One has 128 characters, another one has 256 characters. You might say, okay, well, we're using Roman letters, A, B, C, D. There's only 26 of them. So why do we need 256 things in ASCII? Well, the reason is because we also store in there special characters, ats, apostrophes. We have a lot of other characters that are stored in there. Also, we have to be able to differentiate between uppercase and lowercase. And so we use the ASCII code. Look at it sometime, just Google ASCII character table, and you'll be able to see how our numbers are. They actually can be represented by numbers. String, so what a string is when we take a bunch of characters and stick them together, then that's called a string. And so strings have that ability. You can take small strings and put them together to make bigger strings. We call that concatenation. Now, you can't do mathematics on strings, but you can add them together. We use this word concatenate. So here we got two different strings can be put together to make a bigger string. And when you start playing around with your first programming language, you guys doing programming with Python? Not yet? Okay, well, when you do, you will do that a bit. But when we get to our Python, are you not? 1201? INFS 1201? You doing that? Okay, so they are doing Python programming. In this course, we might do a little bit of Python at the end of the course, maybe. But we have, once we've finished all this. With variables that have a value, which is, or a type, which is integer or a floating point. So in other words, if they're a number, then we can do all kinds of mathematics with them. And so the variable will be stored in a place in the memory, which is unique to that variable. So if we got a thing like this in a computer program, there would be a position in the memory, which is assigned to C, another one for A and another one for B. What would happen is whatever value is assigned to A and B would be operated upon by the computer language. And in this case, those two values would be added together, and then the result would be stored in the memory position, which is assigned to C. And then if you did an output of that position, you could display the result. So for example, if A was 2 and B was 3, and then we applied this in a computer program, then C would end up storing the value of 5, because that's what 2 plus 3 is. Then if we said print C, then we would see the number 5. That's what that's all about. So the idea of a program state, the program state refers to what's happening to all of our variables and constants at this point of time, or at this point of processing in the computer program. And so it's a way of saying, if we could look at what are the values of all of the variables at any point in time, that would show us the computer state. Of course, you can do that. I mean, you can inject into your computing code, and this is what people do as a way of debugging programs. You know, I don't know what's going on with my program. What will I do? Common thing to do is just go back into the program, put a bunch of print statements, especially inside loops, and then you can see what's happening. Print all the variables out at this point, and then you can find out what the error is. Another way of doing that is by hand on paper, which is what we call tracing, where you can sort of just go through line in the computer program and have a table which has all of the variables, and you change the values as they're changed in the computer program. But as I said, if you're actually doing this on a program that you're writing, just a bunch of print statements would work pretty well. So desk checking is what we used to call this. Another word for it is tracing. So tracing, as I said, you'll make a table. In the table will be all of your variables and constants. And every time one of those is changed for the variables, you will update it at that particular line in the code. All right. Recall the flow chart of the program that asks the user to enter, what's that? His age or her age, then displays happy birthday to you. I think that's here, right? So the idea of tracing the program, and again, I apologize for the pen. I do need to bring down a different color pen, I think. But the idea would be is, okay, what is the variable? Is this one? This is the, oh, this was a counted one. This is not this one, sorry. The one that they're asking about had the initializing the counter. And then we, you know, did we get, that was the bigger one. Do you remember the bigger one a minute ago? This is the one with the Sentinel loop. The bigger one with the counted loop went something like, we initialize the variable. So we started, we initialized to 0. Count takes the value of 0. Then we printed happy birthday. then yeah, you could do that. I probably should ask them their birthday first. We got input of their birthday. Input your birthday. And then, so we got that birthday. So what this does is we would, at this point, we would have two variables. We would have a count variable and we would have a birthday variable. So then we would print happy birthday. Then we would do a check, increment the counter. So that's a process. And then we would do the check. So is the counter less than the age? And if it is, then we go back and we print happy birthday again. And if it's not, then we end. So that was the happy birthday counted loop. If we wanted to do a trace of it, what we would do is you have to sort of do the code sort of one line at a time. So you draw on one side, you draw all the variables. So one of the variables there would be birthday. Age, wouldn't it? You have age, and then you have count. Starting the program, the first line, if I number these lines, so there's 5 lines in this program. So line 1, what happens is the count is 0. Line 2, so this is how the program would work. We'd go from line 1 to line 2. We would get their birthday. So let's say their birthday is 25. They say 25, so we got their birthday. Let's not make it 25 because I don't want to go through this loop 25 times. Let's make their age 3. Okay, count is still 0. Then we're going to print happy birthday. So 3, all we do here is we have another line that we'll call output. And so here we're going to say happy birthday. That's output. These things are not changed at line 3. So that's how we do our tracing, is you just update for each line of code as you go. Line 4 would then happen then. Line 4 is increment the counter. So the counter becomes 1. That's what we mean by increment. See, this tracing is pain. It's not my favorite part of programming by a long way. These other things are not changed. The age is still 3. At line 5, we've got a question. These things change. These things are still the same. I suppose we could put another, where I run out of space. Let's put it here, which will be our yes, no. Well, I'm not going to do that. So what happens here is that we test, is the count less than the age? The count is less than the age. So that's a yes. So that takes us back to line 3. We go and do line 3 again. You see how that's working? Because the count is less than the age, we go back to line 3. At line 3, we print happy birthday again. And these things are still, the age is still 3. At line 4, we increment the counter. So the counter now becomes 2. And then we go to line 5. At line 5, this is still 3. This is still 2. And this is still less than that. So we go to line 3. Line 3, so had to go back to line 3. We print. So here we got our happy birthday coming out again. And so the age is still 3. At line 4, we go to line 4. This becomes 3. So then we go to line 5. This time when we go to line 5, it's going to check, is the count less than the age? No, it's not. So then we have to end. Well, I guess you could say that's 6. So I hope that sort of makes sense. That's how we would do tracing. When you do your tracing, you can see what happens to your variables. And that, my friends, seems to be the end of it. Okay, so maybe I'm going to stop recording at the moment, at least.